So the start of the next unit is going to be over solving systems of equations. We're going to look at a couple of different ways to solve systems of equations, including matrices. But let's start with some substitution and elimination, elimination methods by just looking at a system. So let's first talk about what a system is. A system is indicated by the little squigglies in front of a set of equations. Now, what this basically says is that the x's are the same in both equations and the y's are the same in both equations. And depending on how many variables we have, we may have a third variable z. We need a third equation to compare those. So if we have two equations to compare two variables or more, we can solve for those variables because it has to satisfy both equations. In this case, you can see that we have x plus y equals 5, but then x minus y has to be equal 1. Well, we ask ourselves, what two numbers can we add together and equal 5, but if we take the 1 and subtract it, we get 1. In this case, x equal to 3, y equal to 2 works, and that is the solution to this system. Now, that was easily done by just looking at it and kind of thinking about it, but they aren't so easy to see. So let's look at some different methods. We're going to look at two methods today. The first method we're going to do is substitution. So basically with substitution, we're going to take one of the equations. Let's take this bottom equation, for example, and let's solve for a variable. We solve for x. Now, we know that all the x's and y's in both equations are the same as in the other equation. So in this case, if x equals 1 plus y, if I take the other equation, I know that x is 1 plus y. So I substitute it in. And in that case, I have now made it a single variable equation, which I can solve. We get 2y equals 4 or y equals 2. Now, I'm not done because I have solved for one variable. To solve a system, I need to find all unknowns. And so I have to take this guy and use it to find the other variable, which is x. So I already have solved for x here. Substitute in y, and x is 3. So the solution to this system is x equal to 3, y equal to 2. Let's do another example of solving by using substitution with a system. Okay, here's a system here. Now I want to solve for the variable that's easiest to solve for. You can see in this top equation I can solve for y by just subtracting 3x from both sides. Now I need to take that and substitute in for y into the other equation. Okay, and then I'm going to solve for x in this equation because I've now made it a equation of one variable. So x equals 3. I need to solve for y. I've already solved for y up here, so let's go ahead and plug in x. So we have y equals 13 minus 9, y equals 4. So the solution is x equal to 3, y equal to 4. Okay, now that's substitution. The other way is elimination, which I prefer. I think most people do prefer because it works every time. It's not always as easy as substitution, but there's a lot of them that substitution does not work on very easily, so elimination works a little bit better. Elimination builds off the fact that you can sum any two equations in a system. Okay? You can just sum up any two equations in a system, and it's still going to be the same x and y. So for example, let's say with this specific case, we have 2x minus 3y equals negative 16, and negative 2x plus 5y equals 24. When I sum these two up, you can see right here that those guys are going to eliminate with each other. They just go away. So I end up with 2y equals 12, or y equals 6. Now to solve for x, I can plug it into any equation in this system. So I'll just pick the top one. So we have 2x minus 3 times 6 equals negative 16. So 2x minus 18 equals negative 16. I made a boo-boo. Let's go back a little bit. I'm sure you noticed it right here. When you do 16 plus 24, you get 8. Negative 16 plus 24. So y is 4. Sorry about that. So we have 2x minus 3 times 4 equals negative 16. So we have 2x minus 12 equals negative 16. Add 12 to both sides. 2x equals negative 4. And then divide by 2. X equals negative 2. So the solution is x equal to negative 2. Y equal to 4. Okay, that's using elimination. But if you look on this one, it happened to be a nice one where we already had a 2 and a negative 2. Now, what if we don't always have that added up? Let's say I just have any random equation here. I think everyone would agree that if you do something to one side of the equation, you can do it to the other side of the equation, and it's the same equation. So these guys are equivalent. Okay, so we're going to use that fact to help us get the opposites in a certain column, let's say the x's or y's, whichever ones we want to get rid of, by multiplying by something. Okay, in this case, let's say I have this system. Let's say I have 3x plus 5y equals negative 7, and 6x minus 2y equals 10. I don't have any opposites like the last one, but you can see that in the first column, the x's, if I multiply, let me go ahead and do this in red so we can kind of keep up with what we're doing here. If I multiply by negative 2, that's going to make that first equation have a negative 6. Now I have the opposites in that first column, so when I add them up, I get negative 12y equals 24, so y equals negative 2. Once I have it, I can just substitute into one of the other equations. I did the first equation last time. Let's just do the second equation just for the fun of it. I get 6x plus 4 equals 10. Subtract 4 from both sides. So x equals 1. So the solution is x equal to 1, y equal to negative 2. Okay? But that time I only had to multiply one of the equations. Let's look at another example. Let's say I have 3x minus 4y equals 1 and 2x plus 3y equals 12. Now I cannot multiply just one of the equations to get an opposite with another one. So what I end up having to do, which just is the most general form, is get some opposites. So if you look right here in this first column, I want those to be opposite of each other. So the least common multiple between 3 and 2 is 6. So I want one of those to be 6 and the other one to be negative 6. So if I multiply the top equation by 2, that's going to make that positive 6. So I can multiply the second equation by negative 3 to make that negative 6. So that gives me 6x minus 8y equals 2, and then I have negative 6x minus 9y equals negative 36. When I add those two, I eliminate the x's, I get negative 17y, and I get negative 34. If I divide both sides by negative 17, you get y equals 2. And again, I can plug that into one of the equations. So we get 3x minus 8 equals 1. 3x equals 9. X equals 3. So the solution is x equal to 3, y equal to 2. Okay, now let's talk about what we're looking for here. Whenever we graph these things, we're making a line. So when we have two lines graphed, where they're intersecting is going to be the solution. Okay? Now, when we're talking about graphing two lines, we also have the possibility of two lines that don't cross each other. Those are parallel lines. So if they don't cross each other, there's no solution. Okay, so we're going to see what that looks like in a system if those happen to be those two lines happen to be parallel lines. And the other possibility with graphing two lines, we may graph a line, and then we go to graph the other one, and it may look different, but it is the exact same. It's just right on top of it. So there is a solution, but there's not just one solution. It's everywhere along that line. I mean, there's a solution there, a solution there, a solution there, a solution there, so on and so forth. So what we say on these guys are the same line, and that's infinitely many solutions. Okay, so let's look and see what the systems look like. So let's look at this one. We have 3x minus 2y equals 4 and negative 6x plus 4y equals 7. If I go to do the elimination method, I'll multiply that by 2, which gives me 6x minus 4y equals 8 on the top equation, and this on the bottom equation. You see that now I have opposites on the x and y, so I have everything going away on the left-hand side. But on the right-hand side, I have 15. Now, this is an untrue statement. Whenever we have this happen, we say this is an inconsistent system. This is an example of the parallel lines. And we said that with parallel lines there is no solution. So inconsistent systems, whenever we end up with 0 equals something, some untrue statement, and that is inconsistent. No solution. Let's look at the other one. If they're the exact same line, what do you expect to see happen? Well, if everything's exactly the same, we expect to see everything cancel out. So in this case, I need to multiply the bottom equation by 2. Top equation becomes 8x minus 2y equals negative 4. Then I have negative 8x plus 2y equals 4. When I add those, you see everything on the left-hand side goes away, and everything on the right-hand side also goes away. Now that's true, but everything was exactly the same. They just all canceled out because they were the same line. So this kind of system we call a dependent system. And it's not no solution. The last one was no solution. This one is infinitely many solutions. Okay? We'll stop there. Next time we'll go on to three equation, 3 variable systems.